Welcome back. In this lecture, we will be continuing the thermodynamic property evaluation from volumetric data. In particular, we will be looking at the algorithms for vapor liquid equilibria using Phi Gamma approach. Okay. So, we will start with the basic Phi Gamma approach equation, which is this. Okay. And now, what we are going to do is we are going to rearrange this expression in different forms, and that will be useful depending on what particular data are available. So, you can write yi mole fraction in the vapor phase or gas phase as this, or xi in this form. Okay. So, if you consider y here, you take this in a denominator, you get phi ip. So, this is the expression. Okay. Or if you are interested to evaluate xi, okay, you divide this term in the denominator, which is this. Okay. So, these two terms can be evaluated, we can get it from the general expression which we have. Okay. Now, since we know that summation yi is 1 or summation xi is equal to 1. So, we can also use these expressions in order to come up with the following one. So, for this one is the case when we try to use equation 2 and this expression. Okay. So, if we do that, so this is due to yi equal to 1, which will give us this, and if we multiply p both side, we are going to get this expression. So, if this 4, okay, if we multiply p, then this will give us this expression. Similarly, we know that this expression, if we can use this and plug xi from here, we get this expression. Okay. So, this is okay. So, these are the first 6 equations which are going to be extremely useful for us in the later part when we are going to discuss the algorithms depending on whether there is a bubble point calculation or dew point calculation. For when we consider summation y equal to 1, we got p in this expression. Similarly, here, okay, what we can do is we can also evaluate p. We can take out p here, okay, and p is equal to 1 divided by this expression, or in other word, it will be simply the inverse of this. Okay. Now, these 7 equations we are going to try to use it depending on what kind of calculation we are talking about. Now, let us also consider cases where we have to come up with the initial guesses. So, for example, for the case of bubble point where T, where the temperature has to be estimated or initial guess has to be given, then we will be considering, so considering this is a bubble point, which essentially means that information of xi's are given, right. So, the bubble of vapor we have to evaluate at which conditions the bubble is formed. So, if xi's are given, then we can consider initial guess of the temperature at which this is happening or at which this equilibrium exists by taking the mean value or weighted value of this Ti sat, where Ti sat is for the saturation temperature for individual PO components, where Ti can be also related to the pressure of this system by Anton equation. Okay. In addition, we can also consider where P1 sat, if you are just looking at one of the equation, then we can look at here. Since xi's are given, that means we do not know the yi's, so we consider this equation first. And here what we can do is we can take out we can divide this by P1 sat and multiply by P1 sat, okay, take out P1 sat outside, right, and this rest of the things will go to the denominator part, and this can be written in this form. So, P1 sat is x1 as summation of xi gamma I, this term, and multiply with the rest of the term, and this is inverse of that. Now, this is useful because you can just focus on one of the pressure component of one of the saturation pressure of a component, let us say 1, and we use this information to solve problems. Okay. Again, you can connect this thing by the temperature by this Anton equation relations. Of course, B, A, C's are the constants for a given component. Similarly, for dew point, particular temperature calculation, you have to guess temperature. So, we are talking about dew point, which essentially means the composition of the x are unknown, but y's are given. Okay. So, again you start with an weighted value of temperatures of the individual component saturation temperature with respect to the composition in the vapor phase. And here this, since summation x or x is unknown, so you are going to make use of equations where y is available. So, here what we have done is we have taken the p's here. If you rearrange this expression and take out the P1 multiply by the same P1 here, then you should be able to show that the same expression here, equation 7, can be written in this form, particularly relating P1 to this ratios of the P1 and Pi. Okay. So, this is also useful to make use of it. So, remember that equation 7 rearranging would lead to 13. Okay. And for the case of the bubble point, it is equation 5 which allows you to get equation 10. Okay. So, now these are the set of equations which are available for us, and now we should be able to come up with an algorithms depending on what kind of data which we are given. So, instead of going into details, I will just discuss the procedural aspect of it in order to understand how to solve a problem for a given set of data. So, we will consider now for the bubble point. So, bubble point essentially means the information of the liquid are given. Now, it depends whether temperature is given or pressure is given. So, in this case bubble point P means that we have to calculate the pressure for a given temperature and composition. Okay. Bubble point T would mean that we have to calculate temperature for a given pressure and composition. So, let us look at this case which is bubble point P. Okay. So, you read the information of temperature and all composition for all constant. Now, these constants would be Antoine constants for pure liquid molar volume, etc. Okay, because now you have n number of components. So, you have to get the information of Antoine constants which would relate the saturation temperature and pressure, and that is important for us in a set of equations which we are going to consider. Now, remember that since initially we do not have any information, and at the end we are trying to solve, this is the relation of the equilibrium. So, in this case what we are going to do is we are going to start with an approximation. So, we always start with an approximation considering the ideality of the saturation fugacity of component I, that to be 1, that means we consider it to be like an ideal gas as far as the saturation is concerned, and then as well as the we are considering the Poynting correction to be 1. So, this is what we always start with, that set phi I equal to 1 and Poynting correction to 1. Okay, and then we will try to get the more realistic value by using iterations. Now, given this information and as well as you are given T, for a given T and Antoine constant, you can find out for all the component Pi set for all i's. Okay. All right. So, you can also find out phi I set also and gamma I. Okay. Now, phi I set you can find out by using the volumetric information. This is for the pure system, remember that. So, we should be able to directly use the molar volume properties given here for pure liquid volume, and with as integrated with respect to the pressure from 0 to P set. Given that you have calculated Py set, you should be able to get phi I set, and as well as gamma I. Now, gamma I depends only on the temperature, and this is something which we have not given information as far as the models are concerned. So, the activity models we are going to consider later part of it. Okay. As of now, we are just telling, emphasizing that we have to also calculate the gamma i's given that the information is available. So, without going into details of the models, we are just stating that gamma I we can calculate. Now you have the information of phi, you have the information of Pi and phi I and gamma I. You can evaluate now the pressure, okay, from which equation? So, if you look at it, this is the equation 5, xi's are given, gamma I, pi sat you have calculated, phi I you calculated, molar volume informations are available, pi sat is informations available, and of course, the initial value we have considered phi I to be 1. Okay. So, here this is what we have got back here. So, we can evaluate here. Now, initially we have said this to be 1 and this to be 1. So, we get an estimate of pressure from here. Once we have got an estimation of the pressure, we can use yi from here. Okay. So, remember in the first iteration we have got phi I to be 1 and pointing corrections to be 1. Okay. Now, after evaluating yi, you have new information. Now, you can calculate phi I also, because phi I depends on the partial molar volume and properties, and now using the expression which we have derived earlier, we can get phi I also. And of course, you can also get pointing correction because you know the pi sat, p and other information. Now, since if it is the first iteration, then you go back to this 3, okay, and correct this information p. So, you keep doing that until your delta p, the changes in the pressure value in the current iteration and the preceding iteration is much less than some value epsilon, which should be very small, which would be a convergence criteria. Okay. If not, you keep doing this exercise. So, that is how we obtain this pressure as well as the composition. So, this is what we call it bubble point pressure. Okay. Now, there is a typo over here, so this should have been actually 3, 4, 5, 6 and so forth, but I hope that you understand the meaning of this going back and iterating here. So, let us also look at this temperature, this another case which is basically the dew point calculations, where the composition in the vapor phase is given and here the pressure has to be evaluated. That is why it is called dew point pressure calculations or dew P, which we have written in the short form. So, here again the temperature is given, composition of the vapor phase is given, and we have to evaluate pressure and x here. So, what we are going to do is we are going to read this value, all the constants and the molar informations, set this informations to 1 initially, okay, evaluate again the same way as we have done for the pi sat and as well as the fugacity coefficient of the saturation system. Now, since this y's are given, you have to come up with a different equation. This equation would be this one, because y's are given. So, initially gamma is we are going to taking 1, pi sat we know, phi I sat we know, this is 1. So, we got an information of p from here. Okay. So, this is what we got. So, we got the information of p here. Now, xi we calculate, going back to the original phi gamma expression, xi we calculate from here. Okay. Now, again we are keeping the same, like we are keeping gamma is to be 1 in this case and the point and correction to be 1, phi to be 1. Now, we can evaluate phi I and gamma I and pointing correction, considering that we have this information available. We evaluate the phi I again, if this is the first, then first iteration, then we go back to this thing. So, we can keep doing this exercise until delta p is less than some epsilon, which is basically the convergence criteria, and then we finally print out the pressure and gamma. Okay, now the previous exercise was all bubble point calculation, dew point calculation. This is going to be bubble temperature and dew temperature. So, in this case, for the case of bubble temperature, you have the pressure information available and then you have to calculate temperature. Okay. So, bubble again means the composition of the liquid phase is available. So, that and the pressure is given, that is why it is bubble point T, because T we have to evaluate. Now, again read this information, all constants, set this information to 1. So, now remember that you may ask this question, that in this case why we had to keep gamma I equal to 1. Okay. Now, you actually could have simply calculate gamma also as well, because gamma depends on the temperature, but this is one of the simplest way to do that. Here also we have kept the gamma to be 1, but you can evaluate gamma also directly if the models are available. Okay. Here again we are doing the same exercise, that for bubble T, when the composition of the liquid phase is available, we read this information, set all the phi's to be 1, pointing correction to be 1, calculate initial temperature, because temperature is needed by simply they are taking the weighted value of the T sat, evaluate this information, which is now Pi sat divided by P1 sat and phi I sat and gamma I. Okay. So, you evaluate, because now you have the temperature information, you evaluate. So, Pi sat for all the saturation pressure components I's based on the, of course, the Antoine equation, and the temperature is given here now, or is estimated, or initial guess is this. So, once you have done that, we can evaluate P1 sat from here, the new P1 sat, based on this expression, which is nothing but equation 11. Okay. If you recall, this was what was the initial guess for temperature in the bubble temperature calculation. So, evaluate from this, and now using the new T, value of T and Pi sat and phi sat, we evaluate phi y1 from the basic phi gamma expression. Using this information, we can evaluate phi I, gamma I, okay, and Poynting correction, and as well as new value of this. Now, if this is the first iteration, we go back, okay, and do this. So, this is how we can work on it. Okay. Now, similarly, for the due temperature calculation, again let me just go quickly here. Here in this case, it's a temperature we have to evaluate. So, that means pressure and the composition of the vapor phase is given. You read all the information, set initially the phi I gammas and pointing to 1. Initial temperature is from the weighted value of T I sat, okay, the same way as we have done this one. Okay, evaluate the ratios of the P1 sat and Pi sat and phi I sat. Now, P1 sat from equation 13 we are going to use, which was this. Okay, this is again we estimate the P1 sat, because this is estimated, and these are the constant. This is 1 we have considered, this is 1 we have considered, and we have evaluated this. This is 1 we have considered. Okay, you estimated P1 sat from equation 13. Okay, temperature from again equation T, which is a weighted value of T1 sat with respect to the composition. Using the new value of T, we evaluate Py sat, phi I sat, and xi from equation 2. Okay. This is again from the basic phi I gamma expression. Evaluate phi I gamma I, okay, and Poynting correction as well as ratio, and if this is the first iteration, you go back and do that. Okay. So, this is a typical way. So, the major important aspect of this kind of algorithm is that you are basically relying on the phi gamma expression. Now, irrespective of whether it is a dew point temperature or bubble point temperature, what you are going to do is basically you are going to manipulate this expression and make some certain assumption. So, the initial guess becomes an important. For temperature, it becomes straightforward. You take a mean value of that. You make a use of the Antoine equation to connect to the pressure and temperature, which is quite valid because of the usually the logarithmic relation between the saturation pressure and temperature. And then you make use of the phi information, which you connect to the volumetric data, and gamma information, which is activity, using a certain model, which we have not disclosed at this point, but this is the usual algorithm. Now, we are not showing any detailed exercise, because this kind of algorithms are used to solve some more complicated, which usually is not easy to depict using this simple pen and paper. You may have to employ Excel sheet or some MATLAB code in order to solve this much easily. Excel sheet has a goal-seek approach. You can use the function goal-seek to solve iteratively certain solution based on this algorithm which we have shown. Okay, so I hope that this gives an idea how to solve problems related to phase equilibria using Phi Gamma approach and using the set of equations which we have written based on the Phi Gamma expression. Now, in the last few minutes of this lecture, I will just describe a bit on the types of the phase equilibria which we see in the mixtures. Okay, you are well aware of at least this phase diagram or PT diagram for pure fluid, okay, where the you have this saturation vapor line here, okay, which range starts from Tp and ends at Tc. Tc is the critical point, and this is the maximum temperature at which vapor gas can coexist. So, solid liquid line is here, and this is the gas, liquid and solid phases, stable phases. Now, it appears to be simple as far as the pure fluid is concerned, but as we add components, as we introduce mixtures, we have, in addition to pressure and temperature and volume, we have an additional variable called composition, okay, and thus we cannot easily draw typical phase diagram of a binary mixture, for example, okay. But fortunately, the binary phase diagram has been classified by Scott and Van in 70s, okay, and I am going to describe the types of different binary phase diagram which we see in experiments, okay. So, this is a typical binary mixture phase diagrams, and there are different types which have been which has been considered or categorized by Scott and Van. So, using some classification scheme, okay. So, this is type 1, okay. So, this line basically is the vapor pressure curve, and this is the pressure against temperature, just like what you have seen here, okay. This was nothing but the line, saturation line. So, this is the same as this, but here these are for different components, okay. And the dotted line here, okay, is basically critical line. So, in this case for the pure system you have just one point, but for the binary mixture there is a line of critical point. So, that at each point this is the maximum temperature at which the phase equilibria can coexist for a given composition, okay. So, that becomes one point, and so for the you vary the composition, you have a different critical point, and when you connect them you will get a critical line, all right, which range from the end point of the vapor pressure for the pure system to the another one, okay. So, this is the way it has been drawn. Now, in addition to vapor pressure line, critical line, you have three phase line where the three phase coexistence. Again, remember here this is only one point as far as three phases are concerned on a PT diagram, okay. But here there will be line of such points, okay, which is called three phase line, okay, and that again depends on the composition, right. So, this is what we are drawing here, and now different types here would lead to different types of binary mixtures, okay, and this is well described in this paper, okay. So, I will not go into the details because it is a bit messy here, but to just to illustrate, at least to give an idea, what I am going to do is I am going to spend some time on this example of type 1, which is a commonly seen binary mixtures phase diagram, and examples of the methane and nitrogen or carbon dioxide and oxygen. So, type 1 basically is the simplest class of phase diagram or phase behavior, usually seen for mixtures of non-polar substances of a similar chemical type, such as mixture of homologous series such as alkenes, okay. So, here what we have is a PT projection of type 1 phase diagram, pressure on y axis, okay, and temperature on the x axis. So, here the vapor pressure curve of component 1 and 2 are ending in a gas liquid critical point and having a continuous gas liquid critical line connecting the critical points of the two pure components, and this type of the phase diagram you must have seen in some earlier thermodynamics courses, okay. Now, if we take a slice of the pressure, constant pressure line, we have a familiar Tx diagram, which is this. This is temperature, this is x. Now, here what we have is basically vapor up here and low temperature liquids are there. So, there is a dew point line and the bubble point line, okay. And here at this point, if we draw a straight line, that becomes these 2 point represent the phases which are at equilibrium having a composition y, and this is composition x, okay. So, at low pressure below the critical point, either pure component of the critical point, the gas liquid coexistence envelope spans the full composition range. So, this is a full composition range, okay, from the vapor pressure point 1 of component 2 the vapor pressure of component 2, that is what we are talking from this point to this point, okay. So, now if we take consider different lines here. Okay, such that the pressure line now connects to the critical point of phase 2. Remember, this one is more volatile, but at low temperature you see the critical point. So, at low pressure, of course, you get the complete one. Now, if you increase the pressure here such that it is increased to the critical pressure of component 2, the gas liquid critical point of pure component appears at the axis here. Okay. So, this is shifted up here. Remember this, let me just show this. So, this is, as we increase the temperature, you see this is shifted up here. So, this goes up in the direction. Okay. And when this line, the constant pressure line is here, then basically this point is represented by this cross, which means this is the gas liquid critical point of the pure component appears on the axis, and this becomes the region which is critical. That means the two phase region is now constrained from here to here. Now, if you go a little bit up also in the pressure, what you see, this gets away from this axis, and this is bound by this particular critical point, which is here, critical line represented here. Okay. So, that means at higher pressure, now above PC of component 2, the region of gas liquid coexistence retreats from the axis, giving a gas liquid critical point for the binary mixture, which is a point on the gas liquid critical line, okay, here in the PT projection. If you look at higher pressure still, so this is the higher pressure, where we are now above the critical point of both the pure component. The gas liquid coexistence envelope is now bound by two gas liquid critical point, okay, which corresponds to this point. So, these regions are shrinked, and thus it does not span the whole composition range. So, you can clearly see that this phase diagram in binary mixtures, a simple addition of one component creates a lot of different variety of phase diagrams, and hence it requires more in-depth understanding of the variations in different components in order to appreciate the phase diagrams, particularly what you saw just now by changing the variations in the pressure and how that affects the two phase regions, TX diagram. And this was only type 1. The type 2, type 5 and all this have more complicated behavior, and I just wanted to illustrate this without going into details, and the more details of course you can see in that paper which we mentioned here. Okay. But I will stop here, and this will be the end of the exercise on the thermodynamic property from volumetric data. There will be examples or assignments which will help you to work on these concepts, and the next lecture we will start a new topic based on statistical mechanics, a bit to give you an idea about relations of thermodynamic property to the macroscopic informations, and as well as we will be also looking at the different types of intermolecular forces experienced by molecules in systems. Okay, so I will see you in the next lecture.